Hello, everyone, and welcome to another episode of Inside Product. I have with me two very special guests today, Nick and Mohammad. The way I think about them is like Madonna, where they don't even need a last name. They're the Nick and Mohammad of the Silicon One team. And Nick and Mohammad actually run our chip business, which is actually a very, very strategic part of Cisco. And Nick is on the product management side by background. Mohammed's on the engineering side. Maybe I'll have each one of you give the audience a little bit of a background. So Nick, we'll start with you.
Sure. Yeah. So I'm an electrical engineer by training. I was at Stanford in the late 1990s, and all my friends were going off to internet startups. And I wanted to work in semiconductors, thinking that the internet was going to need a lot of chips. And I started out in '99 at a company doing networking semiconductors. And
did you always want to do semiconductors, or you actually happened to get into semiconductors at the time as a happenstance because that was your first job or something?
So that was the idea. Like, I was focused on circuit design in college, and then started out my first couple of years designing chips for networking, and then moved into product management about 6 years out of college. Yeah, but I've been working in networking semiconductors the entire time.
And then you went to a bunch of different companies since then, and the two of you worked together as well.
That's right. We were at MMC Networks beginning in '99 is when I started there, and Mohammad was on the team. And then we had a chance to work together at Broadcom a couple years after that.
That's awesome. And Mohammad?
Well, I wish I was decided to go into engineering in the 90s. It was in the 80s. So I graduated from Purdue University in electrical engineering and came to the Bay Area in the late 90s. I've been in the Bay Area since then in many startups. Actually, I joined 4 or 5 startups. One of them was my own startup, and then I decided to join Cisco.
And we're going to talk a lot about silicon today. And you, the three of us, have spent an enormous amount of time together in the past 2 months. Since I had the privilege of taking over this team. And thank you for all the patience you've shown me, because I'm not a silicon guy by background, and you've been very, very good about actually getting me up to speed. But let's start with, why is silicon so important in networking, and why is it such a strategic differentiator for us to have silicon as a core practice? And then we should also talk a little bit about onboard optics, which you own in addition to silicon. So start with you, Nick, and then we'll actually have Mohammad chime in as well.
Absolutely. So really, at the end of the day, all of the systems that we're building have silicon inside at the core. And most networking companies, when they're looking at how do you build out that system, you have a choice. You can purchase chips from other companies. You can build your own chip as an ASIC, working with a third party as a partner to build that silicon, or you can do it yourself. And Cisco is really in that third category. We're doing it ourselves, and Mohammed's leading the team that's making that possible. And the difference there is that by building it yourself, you can really innovate on the features at a much deeper level than if you're having to work with a third party for that. That means you can integrate the features with your software more closely, and you also have more control over the supply chain, and that you're working directly with the foundries and supply partners. And then finally, when you look at new technology innovation, it's about really having an advanced view and an advanced investment in those technologies that are going to make the next generation platforms possible. So Cisco is doing all of those things, and that's possible because we have that in-house team.
And Mohammad, what would you add to that from your lens on the strategic importance of Silicon One with Cisco?
Well, very few companies in the world can build silicon, especially big, large silicon chips that we're building. Very few. And it takes lots of...
Actually, namely 4, I think, right? 4 at scale.
Probably 4. Not many, as I said. Yeah. It's a handful. And it gives Cisco strategic advantage by being one of the very few companies in the world that controls their own destiny all the way from concept to the supply chain to delivering a final product. This is not something that's easy or trivial. Many companies have tried to build these big devices. Everybody can design them. I tell people, everybody can tape out a chip.
Yes.
Taking it to production is a completely different story, and only very few can do that. Cisco is one of them.
So let's talk a little bit about the range of silicon that we have and the kind of use cases that we solve, and why this is important for a different set of class of customers we have. So we have hyperscalers as customers, we have neoclouds as customers, we have sovereign clouds as customers, service providers, and then eventually all the learnings you get from those four really, really benefit the enterprise as well, right? And we've got networking for both the data center as well as the workplace. And when I say workplace, I mean campus, branch, home office, what have you. What specifically, walk us through the range and like, what is the defying physics marvel that is actually being achieved right now in the industry, specifically as it pertains to what's happening with AI and the upsurge that you're seeing with AI?
Sure, absolutely. So first of all, I think Cisco is somewhat unique in the breadth of the products that we're building all in-house. We have 5 product lines in full production and announced, and more in development on the way. And that spans from enterprise networks, both in the edge and in the enterprise core, enterprise data center, service provider networks, and then in cloud and AI, including scale out and scale across applications. So when you look at that, that's a range of almost 100 to 1 in terms of the fastest chip and the slowest chip across that range. But we're able to do that with a common architecture, which means we have a large amount of software leverage between those products. And then we have a lot of commonality when we're planning our products in terms of the technology that we can apply to build those chips. And so that matters because we're able to look across all of those networks. We can spot what's unique to those networks or what are the commonalities. And then we can build a long-term technology strategy with that vantage point across such a broad set of networks, which I think is one thing that's very unique to Cisco. Your second question in terms of the real technology opportunities that we see right now, or what's special in the semiconductor market now, is that AI is changing the requirements for both the hyperscale cloud as well as enterprise networks. Within the cloud, we see a significant increase in the requirements for bandwidth, lower latency, higher reliability, which is, of course, driven by AI training and inference.
And then more efficient power consumption.
Absolutely. So the question is, how do you build a network comprised of thousands of GPUs or AI accelerators interconnected by that networking fabric that we build? We build that fabric. And how can you do that more efficiently? How can you do it more with better power efficiency? And then how can you enable your customers to take that to market faster? A lot of new opportunities for innovation that we're driving on. Over on the enterprise side, we also see a set of new innovations being driven by AI. Here it's somewhat different in that instead of building out the largest cluster possible, it's about AI happening on desktops, on laptops, agents running outside of the cloud. And it's really changing the way we think about enterprise networks. And that drives a lot of new requirements in terms of the software, which in turn drives new requirements for the silicon, which provides opportunities for new innovations in the product at the chip level.
Would it be fair to say that even though the cycle time on these chips is compressing, and Mohammad, you're so close to this from the engineering standpoint, where it used to be that a chip would take, 3, 4, 5 years to develop. Now you're starting to see cycle times close to 18 months on these chips. But what is happening is, even though the cycle times are compressing, the lifetime value of the chip might actually increase and elongate over time, because we have so many use cases that we can actually start to make sure that you can create variants of those chips that over time, that chip might actually have a much longer lifespan. So do you agree with that firstly as a thesis, and then talk a little bit more about...
Well, it depends on which company is producing these chips. For Cisco, the answer is absolutely yes. Why? Cisco has a unique value that it brings to the end customer. We have a programmable packet processing engine, and that by itself extends the life of the project, the products. In the past, not in the past, even now, companies build what we call hardwired packet processing, which means you have to know what the features are beforehand.
Or you would have to do another tape out and make sure that...
Correct. So if you know the features beforehand, you design for it, you verify for it, and you build the product. The feature changes, you have to retape out. In our case, we don't have that constraint. We have a programmable engine that allows us to add features even after we tape out, and after the part has been in production for a while, a customer needs a new feature, we can add that feature. Now, of course, there are for everything there are limitations, but our engine is a very flexible engine.
But would you agree with the thesis in general, Nick, that our chips that we have today, just like if you think about the H100, it costs more today than it did 2 years ago. The longevity of that chip is much longer, but the cycle time with which GPUs are getting built is much, much faster. And I think the same is true for networking silicon. So do you feel like we're going to have, instead of having a 6 to 7 year lifespan of a chip, maybe there's going to be a 10-year lifespan, maybe a 12-year lifespan of a chip? Is that an accurate thesis to have?
Yeah, I think so. One of the elements that I think we'll see playing out over the next several years is that with such large build-outs happening last year and this year, there's going to be a desire to extend the useful lifespan of that infrastructure. Exactly. And so that means, how do you actually maximize the ROI over an extended period of time? And that might mean deploying a mixture of equipment from this generation, maybe 2 years later, maybe 2 years after that, all forming a shared deployment.
And they just degraduate the workload as they actually get less demanding for the kind of thing.
Exactly. So the idea is not only designing for the latest and the current generation, but it's how do I actually look at a multi-generational approach to building out these deployments and making sure that you can get the most out of that equipment. Often that means interoperability and making sure the features across the network. When you look at the features tops down, there is really a desire for consistency in terms of your telemetry, in terms of how you're actually doing the traffic handling. And the programmability is very special because that allows you to actually drive more consistency across different generations of the equipment, which in turn allows customers to extend the useful lifespan of the equipment that they're deploying.
So we have made our own ASICs for a very long time, but 10 years ago, we decided that we were going to get into the full customer-owned tooling and tool set for chip design, right? So direct to foundry. Walk people through what the benefit of Silicon One is. What is the benefit of having a single platform? And why is that good for an enterprise customer? Why is that good for a hyperscaler? What's the end outcome that you get by having a single platform with Cisco compared to not?
Okay, I'll take the first part and what Cisco used to do and what Cisco does now. Yeah, we used to do. We always did ASIC design or silicon development, but it was mainly ASIC flow. What is ASIC flow? ASIC flow means you do the architecture, the front end design, the RTL coding, the verification, and then you hand it over to another company to build the silicon. That comes with some price, some cost. The cost is not just financial cost; it's also it's not as optimized because the vendor, as an ASIC vendor, wants to make sure they have enough margins for their manufacturing so they can keep increasing their gross margins and squeezing profit out of these devices. But Cisco ended up paying for that somehow because the product is not completely optimized. Mm-hmm. You're leaving something on the table. With merchant silicon, that's another option, is you buy merchant silicon, but the merchant silicon has to appeal to many companies, and you are buying features that you don't need. And still, again, the cost is also higher, and the power and other things, because there are many features in there that you don't need, but you have to take them. Yeah. With the COT, customer-owned tooling, and the way Silicon One is done right now, is we control everything. We don't want a feature, we don't put it in. We replace that feature with something else that's more valuable. So the chip, by
definition, is highly efficient.
It's highly optimized for what Cisco really needs and the features that Cisco is driving to their customer. And you don't have that much wastage in the chip for things that you don't need. In addition to that, obviously, you have higher performance and, in many cases, lower power. And you control your own destiny in the supply chain. You don't have to depend on anyone except the foundry. And you manage your process shifting, the supply demand wherever you need it.
Yeah.
What would you add to that, Nick?
Yeah, I think it's interesting when Cisco made the transition to COT and in-house silicon, definitely it was driven by the benefits that you get from being able to control your own roadmap timing, being able to have a direct interaction with the foundry and the cost benefits and the optimization. What's really interesting is that decision ended up being pivotal to Cisco's participation in the AI transition that we're seeing right now. And so a lot of the success that we're enjoying in AI is really based on that decision to do our own chips. Specifically, what we see in cloud and AI in the hyperscale data center is that the next generation of every AI build out is really driven by what's possible with the next generation of silicon. So that the companies that have that technology in-house that are able to drive those new innovations are really working as partners with the hyperscalers to define that next generation platform. And because we're building the chips here in-house, we're looking at the technology we need, we can really work very closely to anticipate the next generation of AI build-outs. And that, a couple of years later, translates into new business as we roll those out and we deploy those in production. And so that's really been a key part of our strategy.
What's fascinating is the actual amount of defying physics that happens in each one of these chip build-outs that goes on, right? And I mean, talk a little bit about that.
Yeah, so to start with, let's take the G300, which is a product we announced in February. This is our 100 terabit per second switch. And this device is 250 billion transistors. And there's multiple devices that are integrated that Mohammad and the team made possible with the design. And that really speaks to an example of how the next generation of the product is really driven by new innovations in core technology. When we look at what it's going to take to get beyond 100 terabits, it means new reinvention, a lot of new core technologies that come together.
Yeah, this 100 terabit switch, for example, it's...
You said people have to kind of just take a moment and grok 100 terabits per second.
Yeah. If about 7-8 years ago, 12 terabits was a big deal.
Yeah.
Was a big deal.
Yeah.
We're at 100 terabits right now.
Yeah. And by the way, I don't think it's unreasonable to think we will eventually, in the not so distant future, get to 1 petabit of speed and about 1 trillion transistors. Like that is not like
that's not that's
not an absurd ambition to have.
No, that's within reach.
That's within reach. Yeah,
yep, exactly. The technologies that we have to put together, the flows. It's not just tools and just architecture. It's every discipline is now extremely important and extremely specialized, from architecture to design, and the verification effort is huge. DFT is very complex.
Explain for people that don't know what DFT is.
It's designed for testability. If you do not have good DFT in a device, you cannot produce it in high volume and good quality. It's extremely important piece. In the past, let's put it this way, in the early 90s, it was an option to add DFT into a device at that time. And when it was added, it was like, wow, it's amazing. And it was very, very basic. DFT now is a very complex flow that we have to put in place. And without it, you cannot mass produce. And people don't give it enough attention. Cisco pays lots of attention to this.
So why is it more valuable for the customer to have a single platform, Silicon One, versus going out and making sure that every single chip they need is optimized for their particular workflow? Like, well, what do they get out of it, Nick?
Yeah, I think in particular we can look at the enterprise and campus markets. Here you have a lot of different products of different bandwidths, different form factors. You might be talking about your branch office, you might be talking about the edge of the enterprise or the core or the enterprise data center. You really want to have products that are very well optimized for each use case. But when you look at the management of that network,
Yeah.
you don't want a lot of different things. You don't want to aggregate 9 different solutions that each have their own software programming model. So there's a lot of benefit from having a consistent architecture, a consistent programming model across all of those different form factors, but at the same time, having systems that are optimized for their use case in the network. And this is an area where we're seeing the in-house silicon really bring a lot of benefits for our enterprise and campus product lines. I think that benefit is going to continue to magnify and amplify with AI, because with AI, we see a lot of new applications inside of a campus network, inside the workplace network, because it's no longer being driven by the behavior of employees, right? In the past, we'd be looking at what hours are employees working? Are they bringing their own device and connecting to the Wi-Fi over the phone? When you start moving to agents in the enterprise, you're now no longer thinking about human behaviors, but what are the behaviors of those agents?
Right.
That has a huge impact on the bandwidth of the network, on the security concerns. And so the need to have the performance, the need to have that be optimized for different points in the network continues, but the ability to actually have full visibility across what's happening in your network becomes even more important. And because AI is moving so fast, it's really hard to pull together pieces from different places. So having that unified platform becomes critical. And that's really the answer to the question there. It's that the future is about velocity, but consistency in terms of programmability, in terms of managing that network.
Two-part question for you folks is, one is, describe for us the entire family of chips and what different parts of our estate we go out and cover, and what kind of use cases we solve. And then Mohammad, geek out for us a little bit on why the way in which we've architected our chips is actually superior in the market. So let's start with the chips themselves.
Sure. So we use letters to denote all of our different product families. And so I'll start from the highest bandwidth and work down towards the edge. So first we have the G product family, which is built for cloud and AI applications, and it's our highest bandwidth product line. This is the 100 terabit per second flagship that I spoke about. And you often hear it referred to for scale-out applications. The second
And
product...
scale out being that you can actually have multiple clusters within a data center that can get networked.
Yep, absolutely. So the way to think about it is all data centers are a network of GPUs or AI accelerators, and it's the networking equipment that makes those devices behave like a parallel supercomputer.
Right.
And when we talk about scale out, it's about scaling out that those compute resources to form the cluster.
Yeah.
And so that's really where the G series comes in handy, and that's where we're seeing a lot of success with multiple generations.
Rows of racks.
Yep.
Just making sure that they're getting networked.
We picture rows of racks of thousands and thousands of devices that form that cluster is
Right.
being connected by a device like the G. The second is our P series family, and this is targeted for scale across applications. So this is where you have a data center spread across multiple sites. And that's becoming increasingly important because with larger and larger clusters, you may actually exceed the capability of a single building to house that many
Right.
accelerators. That could be because of power consumption, floor space, cooling, a number of different factors say that you want a cluster across multiple sites. When you go across multiple sites, you're talking about connections that span kilometers of distance. We're talking about coherent optics, like you probably spoke about on another session. And you also talk about routing capability, right? You're moving out of the switching domain and into long haul or carrier grade routing. And that's the product that we've built with the P series line. We also provide deep packet buffers, which are necessary when you're talking about those very long reaches.
Because if a packet drops otherwise without deep packet buffers, you have to restart a training run, which could be extraordinarily expensive.
Exactly, and that's really the key there, is that it's relying on the network to be reliable and to not drop packets. And when you're talking about running it across a very long haul link, because it's going across this distance, you technically want to run it at a high level of bandwidth. You want to run it hot, if you will, but you don't want to drop. And packet buffer is what allows you to do that, to simultaneously put a lot of traffic across it without dropping. And so with the P series line, our latest generation is the P200, 51 terabits per second, with those deep in-package packet buffers. And there we're seeing a lot of success with that product line as well. Next, we'll
That's
talk.
for scale across.
That's for the scale across within AI data centers. Next, we'll talk about enterprise data center applications, where we have the E family. And so this one has a lot of the attributes of the G family, but it's right-sized with the right features for that enterprise data center application. You would generally see slightly lower bandwidths. You might see some higher feature scale because you have more of a heterogeneous type of deployment than the consistency you would see in the cloud.
Sure.
And it's really right-sized and right-featured
For the enterprise.
for the
specifically.
enterprise for those
So
applications.
this is where our Nexus switches largely use the E-series family.
Absolutely, that's where you would see that. And here there's a lot of features that we develop within the system level, within the software for the Nexus product family that are supported by that E-series line.
Right.
So this is where you see a lot of the advantages of Cisco having a common platform or a unified platform, full stack with the software, the network operating system software, the hardware design, and then finally the silicon. Like the E-series really plays a part there. Next one we'll talk about is the A series. This is for enterprise access, and so you can picture wiring closet switches, the product line that really built Cisco's product family.
Campus
over the
branch
years.
switching for access.
Yep, absolutely. And so this has been really the core of Cisco's enterprise product line for decades. And here with the A line, we have the optimization, but also the programmability that's needed to provide all of the feature sets for our customers, but also to provide that longevity in terms of new features over time. And then finally, we have the K series, which is our router product family. And this is targeted at service provider applications, but it's also used in the enterprise in some cases where you're spanning multiple sites, where you have to have that routing capability to interoperate with service provider networks.
Yeah. And by the way, the P series is also a routing chip,
Yep.
as is the K series.
Yep, and that's a perfect example where you have two devices with a 10-to-1 spread in the bandwidth. Like, you know, when you're talking about these core optical router applications for between data centers versus enterprise routing, it's a 10-to-1 spread in the bandwidth requirement, but yet we have a common silicon architecture, which means a high degree of software reuse across those platforms.
So, Mohammad, why is it that our chips are better than the competition's in your mind? What is special about these chips, and why are they so uniquely designed architecturally?
We have built an amazing team. We have attracted lots of talent from all over the place. We have flows that are that take silicon to production with, you know, the first tape out. We don't do 2, 3, 4, 5 tape outs.
And why is that important for the customer?
Because that's time to market. It's also based on the quality that Cisco is known for. We build our devices with the highest quality. We don't cut any corners. We do all that's needed to get to production with full suite of tests that we do at every step of taking a chip to production. One advantage that our silicon, as Nick mentioned, we have common IPs in the product that we use across the board. We
Things like SerDes and
SerDes, Max, even the packet processing. It's leveraged from the low end to the high end. So we have lots of leverage and reuse, which allows us to make sure that these IPs continue to improve and continue to be of high quality because they're used in multiple products. One advantage of the silicon that Cisco has that others do not have is we have, as I mentioned at the very beginning, we have a programmable engine. That's one piece of the equation that is very valuable for Cisco. We also have another very unique thing that no one else has, shared buffer. A shared buffer architecture that we have in all of our chips, from all the way from the enterprise, the very low end, to the very high end. That shared buffer gives huge advantages to the customer. As you said, packet drops, absorption of bursts, and so on. Very few companies can do what we do. So the combination of all of these aspects, the engineering, the discipline in execution, the architecture, the IPs that we have developed, the quality that's enforced across all areas in Cisco, just gives Cisco a huge advantage.
And I think one of the other big advantages that most people don't realize is we are a vertically integrated platform that is a co-designed full stack, in the sense that because we make our own silicon, We'll talk about onboard optics in a second. We make our own systems hardware. We make our own systems software. We make our own platform for security, platform for observability, platform for data, our own models, our own applications, our own agents. And they all work in concert with one another. Gives us a huge advantage that no one else has in the market. And so let's talk about onboard optics, because this is an area that from an IP standpoint is pretty important. There's these things called co-packaged optics. There's near-packaged optics. Both are on board. Explain why that's important and what we're doing over there.
Yeah, it's a great topic. And so when we look at optics, for the last many years, optics had typically been deployed as a pluggable module that would be inserted on the faceplate of the system. And there's a movement to bring that optics closer to the switching silicon that's making use of it. Onboard optics or near package optics means placing those optical devices inside the system on the board. And co-package optics means bringing those optical engines right into the chip. Mm-hmm. So in this case, you can picture a device where there are no electrical traces coming out. There are actually fibers coming right out of the package. And the benefit of that is first and foremost power consumption. By having the optics leaving the device closer to the silicon, you can do that with lower power consumption. Yep. And that really matters when you're talking about hundreds of terabits of bandwidth. Being able to reduce the power that you're spending to drive those signals really matters. But this is probably one of the best examples of how Cisco's full platform approach, full stack approach, really makes a difference for product definition and execution. One of the challenges with co-package optics is not only building the device, but how do you build up the entire system using that device? The fibers leave the chip. You need to do fiber handling within the system. You need to do that in addition to the thermal mitigation, like the heat sinks. How does the fibers work with the heatsink? And then when you bring that all together, how are you going to manufacture that cost effectively? Mm-hmm. Then how do you do the reliability on that? If you're approaching that problem as a component manufacturer, think of all the complexity of working out all those engineering challenges and then manufacturing it at scale. Now within Cisco, the team that's working on those type of problems are all daily on calls together, right? We're working side by side. We're really reaching out to identify different challenges and solve them really fast. And really it's about velocity and pulling these solutions together. And so one of the things that I enjoy so much working at Cisco is the fact we have specialists in all those areas in-house.
That's right.
Silicon photonics developers, people with DSP experience in terms of the silicon
digital signal
architectures
processing,
for digital signal processing, package design, the handling of the fiber, system level reliability, system level thermals, supply chain. And so we're able to talk about all of these topics very early in the development process.
And it's not just the supply chain of the chip, it's the supply chain of the entire system.
Of the entire system, of all those pieces that come together. Yeah. And as we're seeing in AI, that's increasingly the critical factor. It's not only building the product, but how do you actually provide it at scale in very high volumes very rapidly? So by working together very early in the development phase, we can build a plan where the engineering is closely tied with the planning for supply chain and in-field reliability.
So I could keep going with you two for a very, very long time, as we have done in many dinners that we've had and many meetings we've had that are day-long meetings. But if you were to tell a customer the things that are the most important things that you want to convey, what would those be from your perspective to the customer as it pertains to our investments we're making in silicon and how that actually impacts systems that eventually gives them better, more reliable networks that they can use so that they can enable themselves with the movement in AI?
Well, I would say whatever Nick just mentioned about the fact that when you get the silicon, the system, the software, the optics, all of it from one place, you know that it's been tested extensively and everyone worked together. It's not like...
It's co-designed.
Everything is co-designed from day one.
Yeah.
By the team in one building or two buildings next to each other. There is one place that everything is coming together. It's very cohesive and it's very well understood compared to anything else outside where you have to take pieces from different places and figure out how to put it together. This is a key differentiator that we have. Cisco has has been known for quality. And knowing that we are putting the optics, the silicon, the system all together, we guarantee the whole system together is of the highest quality. It's not about one component, it's about the whole system.
Nick, anything to add?
Yeah, so I would say that Cisco at its core is really focused on building, deploying, and managing networks globally, worldwide. Whether it's a campus network, service provider, or cloud, it's focused not only on the hardware or the software or the management, but it's all of that. It's really how do you actually deploy and then manage these networks for the needs of the applications running on them. And for a customer looking at their next generation solution, it's important to look at that entire life cycle of that network. And this is really where Cisco is focused. It's on having the right equipment with the right performance for today's needs, but also next generation. It's looking at how you're going to actually manage that network for performance and security and visibility. And it's also about planning for the life cycle in terms of how are you going to mix this equipment with next year's equipment, and then how are you going to manage your overall supply chain as you look at rolling out those networks and then getting them to into market on time. This entire spectrum is where Cisco is focused. And we look at that in terms of the design of our products, and we look at that in terms of how we work with our customers. And so really it's about staying focused on that entire life cycle of the network. And that's really the difference that we can bring, and that's what we focus on in the products that we're building and how we're working with the customers.
I want to end with this, and take the focus away from Cisco for a second and focus on the market with what's happening with AI. What has surprised you the most?
That Cisco is in the middle of this revolution in AI that will solve lots of things like disease and many other problems in the world. In addition to that, what surprises me how quickly now when we use AI at work, we can use AI to help us debug problems. We can use AI to do some coding for us. I mean, it's just changing the way we do business on a daily basis. It's making us more efficient, which means that
we'll have many more chips, hopefully.
We will be able to do many more chips.
Faster.
And we need more engineers to keep driving these chips and getting them to the finish line. So this is a surprise. I never thought that, RTL used to be extremely important. Now RTL is important, but we also can get help from AI to help us with it.
But I will tell you, Mohammad, this one thing that I think a lot of times people misconstrue, and this is more true in silicon than anywhere else. The more you automate with AI, the more human bottlenecks will emerge. And so in some ways, we will move the cycle time faster, but you're still going to have a tremendous amount of need for human dexterity and for human intuition and judgment as you're building these chips. Because what I've learned about the architecture of these chips and how they get designed is you start with a blank slate and then you start to imagine the possibilities of what's going to be the most efficient way that a packet can be processed on that chip. And it's not something that, it requires a lot of instinct that actually is, it's going to take a while for, it's not something that AI is just going to be able to do and replace humans. Like, this is something that is going to require a ton of engineers who are going to get 100x more productive as a result of the use of AI.
This is exactly what I wanted actually to stress, that it removes the areas in our development process that are not, they're not as innovative, for example. It's just, how to do it well, fine, great. The machines can do it for us, and let's move you to work on more innovative solutions with the experience that you have.
Yeah. So if I'm surprised by anything, I think it's the magnitude to which these latest build-outs are happening. I think really this has been the dream. Like to go back to what I started out with is in the late 1990s, the internet is going to need a lot of silicon. As simple as that. And that when you first saw some of the,
you're right about that.
I mean that's but when you think about it, in large part, it took decades for all of this vision to really play out. And so what we're seeing is really a culmination of what a lot of the networking industry has been planning for. And a lot of the concepts that we see getting deployed that are allowing these big hyperscale data centers to get built up are concepts that we've been working on for several years. And I'd say if there's anything surprising, it's just that it's really the magnitude and the scale. Seeing like tens of thousands or hundreds of thousands of connected accelerators with an Ethernet fabric to connect them. It's really exciting to see that happening. But I think just the overall scale, when you talk about industrial compute, I think that's not something I would have anticipated decades ago.
What surprises me the most is the speed at which the market's moving. It's just fascinating to see how much defying of the laws of physics has actually succeeded. Where if you would have asked someone even 20 years ago, will we ever get to a petabit with 1 trillion transistors, they think you're nuts. And now it's actually like, yeah, that's just a matter of time.
Yeah, I think you bring up a great point. I mean, for years, we were talking about Moore's Law
Yeah,
in this
yeah.
concept of just the exponential increase in the number of transistors in a device. But now with multi-die, 2.5D
Yeah.
integration, die stacking,
Right.
now it's becoming a question of other physical assembly challenges, or how do you actually build up these in multiple dimensions?
That's right.
And so it continues, but it's pulling in a lot of cross-functional disciplines to make it happen. And I agree with you, it's moving amazingly fast. And every 2 years, every 3 years is an opportunity for a whole new set of technologies to make the next leap possible. It's absolutely a lot of fun, but it's exhilarating, for sure.
Gentlemen, I think Cisco is lucky to have both of you in these jobs, and you folks are doing a fantastic job at actually innovating for the future of AI. And so thank you for what you do every day.
Thank you.
Great, thank you.